Hello everybody, greetings from Turkey. My name is Meric and I'm a mechanical engineer. Today we are going to make a model analysis and also we will take a look at what is model analysis, what is natural frequency, what is resonance, and also how can we make analytical calculations for the plates to find the natural frequency, and also we will compare our results with the numerical results by using Ansys. So let's start with what is model analysis. Before we get into topic, we need to ask why is vibration important? Because structures are connected to the vibrating systems such as motors, turbines, etc. And also vibration can cause excessive wear of bearings, and also vibration can cause the noise. So let's go back to the topic, what is model analysis? So the definition is basically study of the dynamic properties of linear structures, and also model analysis helps to determine the vibration characteristics. So what are these dynamic properties and the vibration characteristics? These mean that natural frequency and also mode shapes, eigenmodes or etc. By the help of the model analysis we can find the natural frequency. So what is natural frequency, also known as eigenfrequency? So basically, frequency of the system when there is no force or damping factor acting on the system. So that means this frequency is already located at the system without effect. So this natural frequency depends on the mass, stiffness, and also boundary conditions. Why natural frequency is important? Because we need to understand the possible resonance occurring and possible resonance options. So with the help of the natural frequency we will define the resonance, and also the data from the natural frequency analysis can be used as an input data for transient dynamic analysis or harmonic analysis or random vibration analysis, and etc. So what is resonance? The basically oscillation of the structure at high amplitude with specific frequency. So and also natural frequency coincides with the excitation frequency. So this resonance can cause excessive deformation. So what is these two definitions? To understand that, we will take a look at this graph, and in that graph blue line means natural frequency of the structure, you can see this here, and also red line is the frequency of the external force. The black line is the frequency of the whole system, and as you know that from the waves, these distance are the amplitude of the wave, and also we can say that the deformation of the system, we can say that. So if we follow the red line and blue line, as we already told here, natural frequency, so that means blue line coincides with the red line, the resonance occurs in the black line. So when they are matched, the blue line and the red line, when they are matched, the amplitude of the black line is the biggest, and this is called resonance. And this can cause a excessive deformation. As you can see here, the biggest deformation on the system is observed on the black line. So this black line is here. We can say that the resonance when it has high amplitude. So also there is a real life example for the resonance. So there are two systems has their own frequency and they are not matched right now, and this guy is an external force acting on this direction, and now their frequency are starting to match, and we can see that this is the origin, and the deformation rate is increasing because their frequency are matched, and this we can imagine that this is a wave and the wave is getting bigger. So the beginning, the wave is like that, the kit, and after their frequency are matched, the wave, the amplitude of the wave is getting bigger. So this is the displacement of the structure, and this is the deformation of the structure is getting bigger. So this is the very real life example of the resonance. Tacoma Bridge collapse. There is a wind acting on this direction, and the natural frequency of the bridge and the frequency of the wind are matched, and this caused the resonance on the bridge, and finally bridge has collapsed. So as you can understand that resonance is a very important topic for the mechanical engineering. So we will take a look at geometry and boundary conditions to make an analysis. We will make an analysis of the plate. One length is 1 meter, the other length is 2 meter, and the boundary conditions will be all edges are supported, and also the material will be aluminum, and elastic modulus of aluminum 70 gigapascal, and the density of the aluminum 272,700 kilogram per meter square, and also thickness will be 2 millimeter, and the Poisson's ratio will be 0.33. So there is a formulation of the natural frequency of simply supported plate. It is taken from the book. You can find it in the internet. This W means natural circular frequency of the plate, and this is P, you know that, and this D is flexural stiffness. It will be explained in the next slide. And this is rho, is density, and this is H, and this is thickness. M is half wave number of the long edge, this is, and N means half wave number of short edge, and also A and B is the length of the edges. So this formulation in the radians per unit, radians per second, we need to convert this into the hertz. So to convert the unit into the hertz, we will use this formulation. We will divide the natural circular frequency by 2p, so we can reach the natural frequency in hertz. So let's take a look at the meaning of the modes, and also we can say mode shapes and eigenmodes. They are all the same. So the first one is the half wave number of this axis, and the second one, N, is the half wave number of this axis. So if we take a look at the example of mode 3 and 1, there are 3 half waves in this axis and this edge, I mean. So 1 half wave in this edge. So we will make some analytical calculations for natural frequency for different modes, and we will compare them with the Ansys. For example, let's take a look at for mode 1 and 1. First we need to calculate the value, and so this is elastic modulus times thickness, and you know that 70 gigapascal and also 2 millimeter thickness divided by 12 and 1 minus Poisson's ratio squared, and D is 52.37 Newton times meter. So we will take this D value into this formulation, and we will calculate the natural frequency in radian per seconds. So there's P. Also we take the D value from here. Rho is here, 2700 kilogram per meter squared, and also thickness is 2 millimeter, and this first mode will be 1 m value and the second one is 1. The length of the A was 2 meter, that will be 2 meters squared, and that will be 1 meter squared, and so we can find that 38.42 radian per second. So we are converting this into the hertz, and we will find the natural frequency of the plate as 6.115 hertz for the mode 1 and 1. So let's go to the Ansys and let's take a look at this modal analysis as a numerical method. So to make the modal analysis, we will carry the model part into the system. So first, right click on the engineering data and say edit. Then we can apply our material data. So go to the general materials and select the aluminum. So as you remember, our density is this one, and also Young's modulus will be 70 gigapascal. Poisson's ratio is correct, and what else? Okay, there is nothing to do. We can close it. We are done. So go to the geometry and click on the new design modular geometry. So click on the XY plane and look at, and click on the new sketch, and go to the new sketch and click on the sketching and have a rectangle like that, and our unit is meter, that's right. Go to the dimensions and choose length to distance. Okay, we don't need to do that like this. No need. Have a rectangle. Okay, go back, and that will be more basic, and that will be 2 and that will be 1 meter. No, I did it wrong. 1 and 2. Okay, that will be like this, and go to the concept and click on the surface from sketches, because it is thin plate and that belongs to the shell theory. That's why I will choose the surface from sketches and click on the sketch one and say apply, and thickness will be 2 millimeter. So okay, click on the generate and have a plate. So we are done here, and go to the model and click on the update. Okay, right click on the model and click on edit. So we will define the material and go to the surface body and select the aluminum alloy as an assignment. So go to the meshing and click on the sizing. I prefer uniform mesh, and also maximum mesh size will 10 millimeters, and right click on the mesh and say generate mesh. So the meshing is done, and that is very accurate mesh. In model analysis, boundary conditions will be applied, but there will be no force on the system. So I need to just define boundary conditions in the system, and as you remember that all edges will be supported on the plate. So let's go to the model and click on the insert and choose the simply supported and click here the edge and choose the single select and choose all of the edges by clicking Ctrl Alt K on your keyboard. So click on the apply, and now boundary conditions are defined and there will be no force on the system, so I can go through the model analysis. So before we go to the solution, go to the analysis settings and click on it, and there is an option maximum modes to find. We will increase it as a 30, for example. We don't need them too much, but doesn't matter. Right click on the insert and click on the deformation as a total deformation. That will give us the natural frequency as a result. So we will find couple of natural frequency, a couple of nodes. So this is that belongs to mode 1, that belongs to mode 2, and mode 3, mode 4, 5, 6, 7, and 8 is enough for this tutorial. So we will define the 8 modes in this tutorial. You can make it much more, and click on the solve and wait to solve it. So this is solved. There's a graph for the all modes 1 to 3 to the 30, and let's click on the total deformation. And okay, so this unit is on the hertz, as you can see, frequency is in hertz. So to see the all data, click on the tabular data, and you can click on the tabular data and you can see all of the modes and their frequency. So click on the first mode, and as you remember, we find 6.115 Hz for the mode 1 and 1. So mode 1 and 1 means there will be one half wave and there will be one half wave in this edge. So let's take a look at. There is one edge here, one half wave here, and one half wave here. So this is our case, and the frequency is matched with the analytical results, so our method is true. But I am wondering, what if that will be 2 and 1 for the mode 2 and 1? So that will be 2 for M, so that will be 1 for N, as you remember that, M and N. So the natural frequency of the system 9.76 for the mode 2 and 1. So let's go to the deformation 2, and as you can see, M is 2 here, two half waves in the long edge and one half wave in the short edge, right? So the result is matched with the analytical result, so the shape is true, shape is correct. Also, I'm wondering, what if for the M equals to 3 and N equals to 1 for the mode 3 and 1? So the natural frequency of the system will be 15.9 Hz, that will be 3 and 1. So go to the mode 3, and there are 3 half waves in the long edge and one half wave in the short edge. and the result is correct according to our calculation. So what if the mode 1 and 2 and M is 1, N is 2, the others are the same? So the natural frequency of the system 20.79. So go to the Ansys again and go to the mode 4, and there are one half wave in the long edge, and there will be two half waves in the short edge, and 1 and 3 in the short edge, as you can see here, and the result is the same with the analytical calculations. So that means our method is correct, and the analytical calculations and the numerical solutions are matched in the natural frequency. So if you are curious to see, you can apply this for the another mode shapes and for the columns, etc. You can make it in the home. So thank you for watching the video. If you have any questions, you can ask me in the comments. So have a nice day.